what concentration of nickel remains. Okay, so let's first write the equation down for this reaction. So we're starting with nickel plus 6 NH3 goes to Ni NH3 6. Okay, and that is an ionic species. The K sub F is equal to 2.0 times 10 to the 8th. So this is a large formation constant, but there may be a small amount of the reverse reaction. So we need to solve for our new concentration of each of our starting species. So our nickel concentration, once we mix, okay, well, I should put that 2 on the inside. Our nickel concentration is 0.0117. Okay, we're calculating the new concentration, moles per liter times 0.125 liters, and that's equal to 0.014625 moles, okay, of the nickel divided by our new volume. And that new volume is 0.125 liters plus 0.175 liters. And that's equal to 0.004875 molar in nickel. Okay. All right. And so notice that this bottom denominator right here is equal to 0.3. I'm going to go ahead and plug that into our next equation. So let's go ahead and calculate the new concentration of ammonia after we mix them, but before we form the complex. 0.250 moles of ammonia per liter, that's our concentration, times 0.175 liters equals 0.0463 moles per 0.3 liters equals 0.1458 molar. All right, so that's our new concentration of ammonia. Now we can go ahead and build an ice table. So I'm going to go ahead and move over to a new slide so that we can have room to work here. So let's go ahead and rewrite our reaction. Nickel plus ammonia goes to NiNH3 6. All right, and so let's build an ice table. So initial change and equilibrium values we're looking for here. Okay, so we're starting with none. Immediately when we mix, we have none of our complex, okay? But we calculated that we have 0.004875 molar nickel and 0.1458 molar ammonia. We're losing 0.004875. So we're losing essentially all of our nickel, and we're losing 6 times because of the coefficient here, 0.004875 of our ammonia. And basically, we're gaining 0.004875 of our complex. So for every 1 mole of nickel that we lose, we're going to also lose 6 moles of ammonia and gain 1 mole of our complex, okay? So if we let our nickel equal X, because we don't know exactly how much is left, essentially all of it's gone, but we can assume a little bit is left. So we're going to set that equal to X, okay? Then our ammonia is going to be our ammonia left is 0.1458 minus 6 times 0.004875. So we end up with 0.11655 of the ammonia. So we end up with essentially 0.004875 of the complex. So let's go ahead and set our products over reactants equal to our K sub F. Nickel, ammonium, or ammonia complex divided by nickel times ammonia to the 6th. Okay, so our K sub F for this is large. It's 2 times 10 to the 8th. is equal to 0.004875. These are our equilibrium values. And we're going to let X equal our nickel that's left. It's essentially 0, but not quite. 0.11655. Okay, so we know the values for everything else that we can plug in, but we don't know how much nickel is left. It's almost 0, but not quite. So if we solve for X here, our X is equal to 9.7 times 10 to the minus 6. And that is a very small number, but that's the amount of nickel we have left in our solution after we mix and form this complex.